Welcome to Inorganic Chemistry. This is part 4 of chapter 12, Reactions of Coordination Compounds. In this section, we'll look at electron transfer mechanisms. So previously we've looked at how complexes are formed, the thermodynamics for that, and that helps us understand the ligand substitution mechanisms both for octahedral complexes and for squared planar complexes. Now we'll conclude by looking at how electrons are transferred between coordination compounds and the possible mechanisms for that transfer. So this electron transfer mechanisms are very important. Here, for example, is the respiratory chain that occurs in the mitochondria. This is a critical reaction sequence that provides energy for our cells. So you should be, hopefully from biochemistry, familiar with the citric acid cycle, which produces equivalents of NADH. NADH, when it reduces FAD, produces 1 ATP. And this is driven in part by an electrochemical gradient. So the redox potential for NADH getting reduced is at negative 0.28 volts, whereas for FAD to get reduced it's negative 0.22 volts. So there's a gain of energy when NADH gets oxidized and reduces that FAD. Similarly, we get energy gained, or thermodynamic direction for the reaction is for FADH to then reduce the quinone form of coenzyme Q. And then similarly, the hydroquinone can reduce iron 2 or iron 3 plus atoms, 2 of them, in cytochrome B to iron 2. So our electron here is traveling along, and each time it transfers, it's thermodynamically favored reaction, so going downhill here as the electron gets transferred. And these proteins here, like cytochrome B and coenzyme Q, are embedded in the membrane in the mitochondrion, so we also get a proton gradient as the electron flows through here, and it keeps getting shuttled from iron to iron, you see, and then finally it's going to end up in oxygen. Oxygen is a strong oxidizer, positive 0.81 volts for oxygen to go to water, and so there's a big voltage drop here. This is very thermodynamically favored, that helps drive all of these reactions here. And cytochrome A and cytochrome A3, another ATP is formed. And just show you where these ATPs are formed, and another ATP is formed here between cytochrome B and cytochrome C1. So overall you get 3 ATPs out of this reaction, and each time the electron shuttles to the next protein, it's resetting the prior protein. So the iron 2 here gets oxidized to iron 3 as it reduces this iron 3 to iron 2. So this is a cycle. It can just chug right along, producing ATP, producing water from the citric acid cycle. Okay, so cytochrome C, we have actually mentioned this structure before. It's like hemoglobin. There's an iron in a porphyrin ring, and all of these cytochromes are that way. The cytochrome are plant pigment molecules, so that's the name, cytochrome, and then where they come off in the TLC is the letter code. But these redox potentials are tuned for this chain to work, and it's tuned by slightly changing the coordination environment around the iron center, and all of these electron transfer occur through an outer sphere mechanism. So the iron on this cytochrome C1 does not actually directly link with the iron on this cytochrome C. The electron has to tunnel through space between the two proteins, but they come in very close contact due to hydrophobic hydrophilic interactions. So that's an example of an outer sphere mechanism where the electron is transferred through space, where you have metal 1 coordinated, and then it's going to react with metal 2, that is coordinated. It's a different metal here. And the electron has to flow through space. I should have a single arrow, single head arrow there for the electron transfer. It's a single electron that gets moved. So these coordination complexes come together, electron transfers, but there's no link. On the other hand, inner sphere, the electron is transferred through a bridging ligand. So you'd have our metal here, and some kind of ligand is connecting it with our first metal. And the electron can then flow through this sort of molecular wire here. And we'll look in detail at both of these mechanisms. So for the inner sphere mechanism to occur, you need to form that bridge. So the first step would be a ligand substitution reaction, like we talked about in our previous lectures. So you have your metal oxidation state N, and it's going to have to undergo a ligand substitution reaction. So where this X is our bridging ligand, that can come in and substitute for one of the ligands on this first metal to form the bridged intermediate. Okay. Oh, and we lost one of the ligands. Okay. The electron transfer then occurs where you have this bridged intermediate, and we'll call this the precursor complex. And then usually this is rapid electron transfer, and that occurs, let's say we move the electron this way. So this metal gets oxidized and this metal gets reduced. Oops. So we call that the successor complex. L5 successor complex, and then the final step is where the separation of this intermediate back into two separate two separate complexes where the oxidation state is now changed in the products. And this could occur, sometimes this is the rate determining step. If one of these metals is in an inert configuration, then it would be hard for that metal ligand bond to break to form products, and you know, that depending on which ligand is inert, you may or may not get a ligand transfer. Wait, where are we here? So here in this example, the ligand transferred. It was on this metal, but in the product it's now transferred to this metal, the oxidized metal. That's not always the case. You have another option here, right, where you could, that would be if you break this bond. You might break this bond instead, where the bridging ligand goes back to the original metal. If this metal is now in a labile configuration, this bond readily breaks, leaving that as the product. So ligand transfer would certainly be indicative of an inner sphere mechanism, but lack of ligand transfer does not eliminate ligand or inner sphere mechanism as the possibility. Another way to measure the possibility of inner sphere electron transfer is to look at the nature of the bridging ligand. So the bridging ligand needs to have a lone pair, extra lone pair. So for example, the fluoride, Lewis dot structure, plenty of lone pairs that could be bonded to two metals, for example. Same, hydroxide has two. Ammonia does not. This reaction measured here is actually outer sphere. And we'll talk about outer sphere mechanism next. But this is included in the list here as a comparison of the rates. Here the thiocyanate ligand has what we would call a remote attack, because the extra lone pair is on the other end of the ligand. It's not on the same. This is attached to the metal. This is on the other end of the ligand attached to the other metal. It's not coming from the atom that was directly bonded to the first metal, so we call that a remote attack. But you can see here that the trend, the rate constant, increases as we increase the ability of the ligand to form a bridge. So fluoride is small, it has extra electrons, but that's going to be really hard for those two metal ions to bond to it simultaneously, whereas chloride is larger and so easier to bridge. Hydroxide is a better Lewis base, so we'd expect it to undergo that ligand substitution more readily to form that bridge. These are also strong bases, and with that remote attack, that kind of maybe helps with sterics. The metals don't have to get so close together. So we can kind of understand how this trend would work, and the presence of a trend, we change 4 orders of magnitude, would be indicative that this redox reaction occurs by an inner sphere mechanism. We also had ligand transfer, which helps indicate inner sphere mechanism, and we also had something happen here where our cobalt, this is cobalt-3 complex, here it got reduced to cobalt-2, and cobalt-2 is labile, So not only did it lose this bridging ligand to the cobalt cyano complex, it also lost all of its amines to the solvent, water. So we ended up with this product, which again may or may not be indicative of an inner sphere transfer, because cobalt 2 plus is labile no matter how you got to that point. Okay, so let's consider now the outer sphere mechanism, and this comes from Marcus theory, which states that unlike, well, before we had 3 steps in the mechanism, here we're going to propose 5 steps in the mechanism. Reactants diffuse together, which would have to occur for inner sphere as well. The bond distances change to become more product-like. We'll look at that in more detail. It's a little different than what we did before. Before we had to do ligand substitution. The solvent shell reorganizes. We didn't mention that before, but that would also have to occur with inner sphere, that you're changing the dipole and the solvent dipole attractions are going to change, so that there's some kinetic problems that the solvent has to move around. And then the electron transfers, and then the products will diffuse away. So let's look more specifically at this bond distance issue. So here we have an example of a self-exchange redox couple, chromium-chromium redox couple, and I just put an asterisk on this chromium 2 in the reactant side so we could track where it was in the product side, because otherwise it looked like we didn't do anything. And you could do this experiment like isotopically labeling the metal, for example. Okay, and here we have what we call a Morse potential diagram, which should look familiar from P-Chem, where this is our metal ligand bond distance, and so this would be the equilibrium bond distance for the chromium 3, and this is the equilibrium bond distance for the chromium 2 plus, because as you can imagine, the chromium 3 plus with the higher charge is going to pull in those ligands closer together. And so if the ligands pull apart, that weakens the bond. That's not as stable. Energy goes up here. And if we get close together, we start to have Born repulsion between atoms, so energy goes up quite quickly. So that's our Morse potential diagram. So since our equilibrium distances are different, if we tried to, say, reduce the chromium 3 here without making any change in the metal ligand bond distance, we'd end up in a very excited state here. So this is the reduction, and that would be thermodynamically unfavorable, but this is what we'd expect, that electron transfer occurs rapidly compared to atomic motion. This is the Franck-Condon principle. Get the spelling right here. Franck-Condon principle is that the electron transfers faster than the atoms can move, or the nuclear framework changes, and that makes sense. Electrons are small and fast, and so that makes sense, but that's going to give us a highly energetically unfavorable situation. Meanwhile, if something's getting reduced, something's getting oxidized. So our chromium 2 getting oxidized is also going to end up in an excited state here. So what would be better is if the metal ligand could move before the electron transfer. And here where the Morse potential curves overlap, that would be the optimal metal ligand bond distance for electron transfer. So while the electron could do this in terms of kinetically very quickly, it's going to create a huge energy barrier, and so that's not going to happen. Whereas here, yes, it's going to take some energy to change those metal ligand bond distances, but that happens with vibrations, and so occasionally you'll get where the metal ligand bond distances are the same on both complexes, easing the electron transfer. And we can show that by looking at the activation energy. So you've seen this reaction coordinate diagram before. So for delta G on this side and reaction coordinate on this side. And basically what we're going to see is that our energy of activation is where the the chromium 3 plus Morse potential diagram overlaps with the chromium 2 plus Morse potential diagram, and so this value here is our energy of activation. So the energy, that activation energy depends on the energy required to move those metal ligand bond distances. There's some other factors as well, so includes the metal ligand bond distances, which we saw in the previous slide, also includes solvent rearrangement, or solvation, I guess you could call it. And also, though, we also have to look at the d electron, I guess you call it the ligand field stabilization energy. So chromium 3, the configuration would be T2G, 3 electrons in the T2G, whereas chromium 2, where does that 4th electron go? Water being weak ligand, it's going to be high spin, so it'll go up into the EG. So that's going to add some activation energy to get that electron to transfer up into the higher energy d orbital. And so metal ligand distances are an important part, but also these other effects contribute to the energy of activation. And indeed, this particular redox reaction is very slow. Okay, well, what if we have, that was self-exchange or self-redox, what if we have a cross reaction where we have two different compounds reacting together in a redox reaction? And so we could show our reaction coordinate diagram, but now we have a change in Gibbs free energy from the oxidized reactant and the reduced product. And so there's a change in enthalpy for the free energy for the reaction, but we also have, and so our energy of activation here is going to be greater than before because we've shifted that Morse potential well. So here delta G for the reaction is 0, so the only energy of activation is this little bit to move the metal ligand. Mostly, there's other things here, but if we change delta G, we shift where that Morse potential diagram is going to intersect, and that actually increases or decreases our energy of activation. So this relationship between energy of activation and delta G is another example of linear free energy relationship. So the degree to which this delta G double dagger, the activation energy, depends on delta G naught, the energy of the reaction, we can approximate by a formula that Marcus came up with, the Marcus-Cross relation, which says that the rate of the cross reaction, so reactant 1, reactant 2, is equal to the rate of self-redox for reactant 1, self-redox for reactant 2, the equilibrium constant for the cross reaction, because the equilibrium constant is related to delta G naught, as you recall from that relationship, and a factor which is approximately 1 when delta G isn't too large. And if delta G is too large, this linear free energy relationship breaks down. And then take the square root of that. So how to use the Marcus-Cross relation. So if we go back and look at the same cobalt-Bipi complex that's going to oxidize a cobalt-Terp complex, the equilibrium constant for this reaction at this measured temperature is 3.57. The self-redox for the Bipi is 9 per moles per second rate constant. The self-redox for the Terp, the rate constant is measured at 48 per moles per second, all the same temperature. So then if we plug these values into the Marcus-Cross relation, we will calculate or be able to estimate the rate constant for this reaction. So this is the rate constant here and equilibrium constant here. So the rate constant we could estimate as being 9 times 48 times 3.57 times 1, square root of all of that equals 39 per moles per second, and the measured rate constant is at the same temperature 64 per moles per second. So this is within a factor of 2, so that is considered a favorable agreement, and actually in this case if you're within, let's say, a factor of 5 or even more, this is evidence that an outer sphere mechanism is occurring. So if these your estimated rate constant is similar to your observed rate constant, that's evidence for an outer sphere mechanism. Again, this is indirect evidence. You're not seeing exactly what's happening, but based on the theory, that would correspond with what we'd expect. Okay, so those are the two main mechanisms: inner sphere and outer sphere for electron transfer. There's other things that can occur. You can have solvent effects. Solvent can get involved in the redox reaction. You can have ligand based redox reactions. So your ligand could get reduced instead of your metal, or your metal could get reduced by the ligand, for example. And we don't have time to go into all of those. I just want to mention another possible complication, which is how the pH can affect the electron transfer reaction. So if we want to look at, say, redox reaction, self-redox maybe, for iron hexaquo reacting with as a oxidizing agent, we can recognize that this iron 2 complex is an aqua acid that we learned about earlier in the semester. So in the presence of water, it can lose a proton, acting as acid to leave a hydroxide bound to the iron and the hydronium ion. And the hydroxide, now we have a good potential bridging ligand because we have those 2 lone pairs on hydroxide. So now if this aqua acid is in a basic solution, we're going to form this hydroxide ligand, possible bridging ligand, and so now we could have inner sphere electron transfer, whereas before with the hexaquo the preferred mechanism is the outer sphere electron transfer. So when we look at this, say, self-exchange of the iron, the observed rate constant is going to depend on the pH, or the hydronium ion concentration. So we'll have the outer sphere mechanism contributing one step, and then the inner sphere contributing part of the reaction depending on pH and the acid dissociation constant for the aqua acid. So Ka for this part here. Okay, so that's all the time we have for discussing electron transfer reactions. So thank you for your attention, and actually this concludes our course in inorganic chemistry.